Imagine this. A routine task. Something your team has done, maybe, I don't know, countless times, perfectly. You're confident, you're experienced, and then boom, everything just goes sideways. A major incident, not from one big failure, but like a whole cascade of small things. That's exactly what we're diving into today. The 2003 fuel cleaning incident at the Paks Nuclear Power Plant in Hungary.
Yeah, and for this deep dive, we're relying heavily on an IAEA briefing document. It gives this incredible, almost minute-by-minute account. It's really quite something. So our mission today, unpack how these misjudgments, this new tech, and just immense pressure all snowballed into a serious nuclear event. And maybe more importantly, figure out the bigger lessons here about safety culture, oversight, stuff that matters way beyond just nuclear power. Okay, so let's unpack this. Let's go right back to the start. What was the actual problem Pax was trying to solve? What kicked this all off?
Well, the root issue was magnetite, deposits of it building up in the primary circuit of the reactors.
Magnetite, like rust. Sort of, yeah, iron oxide. And it wasn't random. It was actually a result of large-scale chemical decontamination they'd been doing. A lot of it, actually.
How much is a lot?
The tech was used 24 times across the plant, and in 2001 alone, 14 times, mostly linked to replacing feed water distributors in units 1, 2, and 3. So think of it maybe like a radiator in your car getting clogged up. These deposits, they reduced efficiency, caused power loss in those first 3 units.
Ah, okay. Makes sense.
Unit 4, interestingly, wasn't affected. Different biological shielding.
Right, right. And we should remember, Paks wasn't some, failing client. They had a really outstanding operating record up to this point.
Absolutely. They tackled thousands of problems successfully, so there was this inherent confidence, maybe overconfidence.
That they could handle this too. You can almost see how they do feel that way,
Exactly.
So they decide to clean the fuel to get rid of this magnetite. But they made a specific choice: clean at X-core, outside the reactor in the spent fuel pool. Why there?
The main driver was reactor safety. They wanted to avoid any chance of the cleaning chemicals damaging the actual reactor vessel.
Okay, caution. That sounds reasonable on the surface.
And look, it wasn't totally new ground for them. Between 1999 and 2001, Siemens had actually done chemical cleaning there.
Oh, really?
Yeah, successfully cleaned about 170 cold fuel assemblies. That's fuel that's been cooling for a while, not much heat. They used a smaller 7-assembly tank for that.
Cold fuel. Got it. So what changed in 2003?
Well, in 2003, Framatome ANP got the contract for Unit 2, and this time the plan was to clean hot fuel assemblies.
Hot fuel, as in straight from the reactor.
Exactly. Still generating significant heat. And that required a much more complex thermodynamic analysis.
Yeah.
A whole different beast.
Okay, here's where it gets really interesting, isn't it? Because I read there was this immense time pressure. Like, they were way behind schedule.
That's absolutely critical. Huge time constraints. Delays in just evaluating the cleaning options meant they had very little time left for the actual design, construction, and crucially, approval of this new cleaning system for the hot fuel.
And that kind of pressure, it rarely leads to good decisions, does it? What did that do to the design?
It directly led to some, well, frankly, critical design mistakes by the contractor for this new, bigger tank. It was designed for 30 hot assemblies.
Okay, what kind of mistakes are we talking about?
Multiple things. The pump capacity for cooling, when the system wasn't actively cleaning, was just inadequate.
Not good.
They also seriously miscalculated the water flow needed just to keep the fuel cool. No backup power for some key components.
Wow.
And the physical layout, the inlet and outlet water pipes, were put way too close together, basically creating a short circuit for the cooling water.
So the cool water goes in and comes right back out without doing much.
Pretty much. And incredibly, no internal temperature or pressure sensors inside the tank itself.
No sensors. How would they even know what was happening inside?
Exactly. They were relying on external measurements and calculations. And here's maybe the most startling part.
Go on.
Their own calculations showed that if cooling flow was lost, the water inside could start boiling in just 12 minutes and 9 seconds.
Wait, say that again? 12 minutes.
12 minutes and 9 seconds. That's the window they calculated.
That is incredibly short. I mean, impossibly short for reacting in a nuclear facility.
It absolutely is.
Yeah.
It meant the design didn't meet standard single failure criteria. But maybe the most critical failure.
Yes.
The workers' emergency procedures, they never mentioned this 12-minute window. The operators on the ground had no idea how little time they actually had if things went wrong.
Hold on, 12 minutes and 9 seconds, and the operators didn't know? How? How does that happen? How does that critical piece of safety information just not make it into the procedures?
Well, it points to a massive breakdown, doesn't it? A breakdown in translating engineering knowledge, the calculations, into practical operational safety.
Like the engineers knew, but the information got stuck somewhere.
Essentially, yes. That vital, terrifyingly short time frame just didn't filter down to the people who needed it most, the ones who'd have to react in an emergency. It's a classic, and in this case, potentially catastrophic, example of knowledge not reaching the front line.
That's genuinely chilling. Okay, so let's walk through what happened on the day itself. April 10th, 2003. Keeping that 12-minute blind spot in mind. Things started okay, didn't they? They cleaned some batches of cold fuel, no problems.
That's right. Several batches of cold fuel went fine. Then they did one batch of the hot fuel, also successful.
Okay, so far so good. Then what? Then comes this. Fateful decision. A very human decision, made under pressure, it sounds like, after they finished the second batch of hot fuel.
Correct. The refueling crane they needed to move those hot assemblies back into the main spent fuel pool wasn't available.
Just unavailable. Bad timing.
And their shift was ending. So, faced with this problem, the workers decided to just leave that batch of hot fuel sitting in the cleaning tank overnight.
Overnight. The really hot stuff.
Yes. Plan was to move it the next day. Seemed like a practical, if maybe slightly inconvenient, solution at the time.
But with that flawed design.
Oh boy, exactly. That decision, combined with the inadequate cooling design, had immediate severe consequences. The fuel started heating up fast.
Because there wasn't enough passive cooling.
Right. And as the temperature and pressure climbed inside that sealed tank, it started forcing more and more of the cooling water out through that badly placed outlet pipe. A feedback loop.
Getting hotter, losing coolant.
Vicious cycle. The fuel temperature just skyrocketed. It reached about 1,500 degrees Celsius.
1,500 degrees.
Yes. Hot enough that the rubber seal on the tank's lid just melted.
And then?
Then radioactive gases, krypton-85 and iodine-131 mainly, started leaking out. They bubbled up through the water of the spent fuel pool and got into the air of the reactor building.
So alarms must have started going off everywhere.
Oh yeah, radiation detectors went off. The krypton-85 levels spiked around 9:50 p.m.
What did the plant do then?
The supervisor ordered the workers out of the reactor hall around 11:30 p.m. And then, about 15 minutes later, they started up the venting fans to try and clear the contaminated air.
Okay, so alarms blaring, radiation leaking. They know something is seriously wrong inside that tank. What was the next move from management?
Well, they needed to understand what was happening, so management made the call to open the lid of the cleaning tank.
Open the lid of the tank with 1,500-degree fuel inside.
That was the decision, to try and assess the situation. But when they lifted that lid, the surrounding spent pool water, which was much cooler, around 25 degrees Celsius,
Rushed into the superheated tank.
instantly caused a massive violent steam explosion.
Oh my God.
Powerful enough that it just shattered all 30 fuel assemblies inside the tank.
Just shattered them. And they wouldn't even know the full extent of that immediately, would they?
No. It took about a week. They finally got a camera inside the tank.
And what did they see?
Severe damage. Most of the metal casings, the zircaloy cladding around the fuel was just gone, destroyed. They described it as a rubble bed of metal bits and pieces.
A rubble bed inside a nuclear fuel cleaning tank.
Yeah. The fuel pellets themselves, the uranium dioxide, were cracked, but crucially, they hadn't actually melted.
Small mercies, I suppose. And this whole event, it caused some confusion with the safety ratings too, didn't it? The INS scale.
It did. Initially on April 11th, it was rated an INS level 2. That was based mostly on the radiation levels inside the building.
Okay.
But then, about a week later, April 17th, they upgraded it to INS level 3. That higher rating reflected the actual fuel damage caused by the loss of cooling.
And changing the rating like that probably didn't help public confidence much?
No, it definitely caused confusion and likely eroded some public trust, at least initially.
So in the immediate aftermath, investigations start flying, right? Paks does their own, the contractor Framatome, the Hungarian regulator IAEA.
That's right. Paks submitted its report pretty quickly, even published it online. Framatome did theirs. IAEA, the regulator, had its final report by the end of May.
But given how serious this was, and the public reaction, the Hungarian government wanted another layer of review.
They did. They requested an independent expert mission from the IAEA, the International Atomic Energy Agency. Their final report was expected by the end of July.
Okay, so what did the IAEA, the sort of independent international eyes, find? What were their key takeaways?
Well, what's really fascinating, and maybe the most damning insight from the IAEA,
Yeah.
was this fundamental misjudgment of novelty.
Yeah.
Paks was so used to routine stuff, they just failed to grasp that this hot fuel cleaning was new and different. They didn't translate the safety assumptions from paper into the actual design, the procedures, the training.
So the knowledge existed, but it didn't connect to the real world.
Precisely. That critical knowledge just didn't reach the point of execution. They also highlighted the poor design analysis, a real lack of understanding of the technology involved.
And the reviews.
Inadequate. Both the independent safety review by Paks itself and the safety review by the regulator, IAEA. The IAEA felt HAE's licensing process was too complex and just didn't meet international standards, especially for something novel like this.
So multiple layers of oversight failed.
Pretty much. And the root cause analyses done by everyone involved, Paks, Framatome, HAEA, the IAEA, found them all lacking.
How so? Pointing fingers.
Basically, yeah. Paks blamed Framatome. Framatome blamed Paks for not following procedures. The regulator, HAEA, found fault with both the plant and the contractor, but seemed to find very little fault with its own processes.
Not surprising, maybe.
The IAEA also noted a failure to actually verify the contractor's claims and just not enough technical detail in the licensing package. The regulator just didn't seem to grasp the safety implications of this modification.
And the INE's scale changes we talked about.
Yeah, the IAEA confirmed that the initial changes really hurt public confidence. Oh, and in the immediate aftermath, some managers of Paks were removed or demoted.
Right. So if we take a step back, connect this to the bigger picture, how do these lessons from Paks translate, say, compared to the U.S. nuclear regulatory environment?
It's a really interesting comparison. The U.S. has specific regulations like 50.65, the maintenance rule, and 50.59 for design changes.
Rules that would have applied here.
Almost certainly. They demand much tighter controls, especially for something with such a high potential risk like that tiny 12-minute boiling window. That would trigger major scrutiny under 50.59.
And the overall safety analysis.
The U.S. system hinges on the Final Safety Analysis Report, the FSR. It looks at the whole plant, how systems interact. The Hungarian system at the time, more Soviet-era based, tended to license individual components.
Without fully seeing how they connect.
Yeah, potentially missing those crucial system-wide interactions.
Yeah.
This cleaning system was a modification, and its relationship to overall plant safety wasn't fully analyzed by the regulator in the way a U.S. FSR update might require.
What about the human factors, like relying too much on the contractor or that overconfidence we mentioned? Does the U.S. system regulate that?
Not directly, no. There aren't specific rules saying don't be overconfident or don't trust your contractor too much.
Right, how could there be?
But the expectation woven into the regulations is that the licensee, the plant operator, is ultimately responsible. They must rigorously review contractor work, maintain independent technical capability, and foster a strong safety culture that encourages questioning and avoids complacency.
So the Paks incident really showed a failure on multiple fronts, though.
Absolutely. It wasn't one thing.
Yeah.
As the IAEA implied, it was a breakdown of almost every safety barrier. Design, procedures, training, independent review, regulatory oversight.
A cascading failure.
Exactly. If even one of those barriers had held properly, the outcome might have been very different. It really underscores why that defense-in-depth philosophy is so critical.
And the public confidence piece. That must have been huge. You mentioned the INES confusion, but also that the IAEA review actually helped restore trust. How did they manage the communication?
They went into overdrive, basically. It was a massive, comprehensive communication effort by Paks and the authorities.
Like what?
Okay, get this. Information sheets faxed daily to government bodies, media, even 72 mayors in the local area. They set up a special SMS text message system to give mayors instant updates.
Wow, SMS in 2003 for emergency comms.
Yeah. All press releases went straight onto the plant's website. They handled over 300 direct press requests, issued over 1,500 press releases in Hungarian,
1,500.
plus public hearings locally, parliamentary hearings, a press conference held inside the reactor hall to try and show transparency.
In the reactor hall. Bold move.
And they even delivered a dedicated information brochure explaining the situation to 20,000 local families. It was an all-out push to be open and regain trust after that initial stumble.
That is incredibly extensive. Shows how seriously they took the public trust aspect. So after all that, after the explosion, the investigation, what was the immediate situation at the plant? What were the plans going forward, say, as of that IAEA briefing in July 2003?
By July, the immediate crisis was over. The situation in the affected Unit 2 spent fuel pool was stabilized. They had long-term cooling set up for the damaged fuel using multiple pumps.
Okay, so contained.
Right. The radiation levels were stable and working conditions in the plant were considered normal. outside the immediate recovery area, obviously.
In the recovery plan, what were the next steps?
The main priorities were to keep that damaged fuel assembly stable and cooled, completely isolate the Unit 2 pool from Unit 1's adjacent pool, and then figure out how to safely package and dispose of the damaged fuel debris, that rubble bed.
A big job.
A huge job.
Wow.
They formed a dedicated recovery team with experts from Paks itself, the contractor Framatome ANP, and also TVEL, the Russian fuel supplier.
And longer term, for the other reactors that had the magnetite problem.
They were looking at several options for Units 1, 2, and 3. One idea was just operating without fuel cleaning, likely at a lower power level.
Except the efficiency loss.
Or potentially cleaning the fuel inside the reactor pressure vessel, which they'd initially avoided. Or maybe trying X-core cleaning again, but with a completely redesigned, properly analyzed, and approved tank and process.
Learn the lessons and try again, properly this time.
Basically, yes. And the whole incident, the technical details, the recovery, it was all going to be discussed at a technical conference later that year. Sharing the lessons learned was clearly a priority.
What a journey we've taken today. Really shows how something that seems like straightforward maintenance, cleaning fuel, can just unravel a whole chain reaction, really, of flawed design, communication gaps, human decisions under pressure, and, breakdowns and oversight.
It really does hammer home the need for that layered safety approach, doesn't it? Rigorous review, yes, but also fostering a culture where people feel empowered to question things, especially when dealing with something new or operating under the gun.
You can't just have safety procedures on a shelf.
Exactly. It has to be lived, breathed, constantly questioned, and improved, especially when you introduce novelty or face unusual pressures.
Which brings us to a final thought for you, our listener. Thinking about this Paks incident, what are the hidden vulnerabilities in systems you rely on? Things maybe you consider routine or proven in your own work or even daily life. And maybe more importantly, how does your organization foster a culture that doesn't just react but anticipates the unexpected? A culture that questions assumptions even, or maybe especially when the pressure is on. Something to think about.